in this first, what I'll call, this is my first real linear algebra video. Let me write that down. Linear algebra video. I want to introduce you to some concepts that you're going to see over and over in linear algebra. And if they're not introduced to you properly in the beginning, they can be very confusing. But hopefully over the course of this video, you'll understand that they're pretty straightforward ideas. And if anything, in linear algebra, the field or the gods of linear algebra are kind of experts in, to some degree, stating simple and obvious things in convoluted and Byzantine ways. But it does that for a reason. It gives it mathematical rigor. So the first thing I want to introduce you to is kind of the set notation for real numbers, and then multiple dimensions of real numbers. So if you ever see this, an R with kind of an extra backbone like that, or sometimes it's written as just a really bold-faced R, if it's maybe typed in a book, a really bold-faced R, all this just means the set of all real numbers. And I haven't done, and I probably should make a few videos where I classify numbers by reals and complex and irrational and rational and whatever else. But my brain, and there's actually very formal ways of defining the set of all real numbers. But the simple thing for me is all numbers except complex ones. So this is the same thing as everything but complex numbers. So pi is a real number. E is a real number. Square root of 2 is a real number. 3 is a real number. Minus 3 is a real number. Minus pi is a real number. But 1 plus 2i, not a real number. Not in the set of reals. That's a complex number. So everything but complex. So pretty much all regular numbers that you ever dealt with before you learned what I was. That's the set of real numbers. Now, the next thing you'll see in when you start discussing linear algebra is someone will write, they won't just write the set of all real numbers. They'll write R. I'll just write it generally. They'll write Rn. And you're like, gee, what is that? Are they somehow taking the exponent of all of the real numbers? And actually, on some level, that is what they're doing. But what they're saying here is you're taking the set of all ordered sets of real numbers. So what do I mean by that? So let me do an example where I don't just have Rn. So R2 is the set of all lists of real numbers. And let me make one of the lists. So let's say, this has one number and then it has another number. So it's the set of, let me write it this way. So I can write in set of notations. It's the set of all, we could call these tuples. Sometimes it's called a two-tuple. I want you to two-tuple, which just means just a list of two numbers. That's all it means. It just means a list of two numbers. So R2 is the list of all ordered two tuples, so all ordered lists of two numbers. Let me actually write down the word ordered, because that's important. So ordered list of two tuples. So for example, this would be, well, let me write it this way. This would be a different, when I say ordered, I'm saying that this is fundamentally different than that these aren't the same two tuple. Each of these is a two tuple. But R2 is a set of all two tuples, such that, that line there just means such that, or maybe for which, such that each of the numbers, and I'll write it this way. I could just write, well, I could write it a couple of ways, but I'll write in the harder to understand way, just so you get used to it. Such that xi is a member of the reals. So member of, that's what this member of, that's what this little character means. So that each xi is a member of the reals. So what do you mean xi? Well, xi just means any of these x's. And I'll write for I is less than or equal to 2 and greater than or equal to 1. And I is an integer. Now, I could have written this a bunch of different ways. And you might, this is almost silly how much effort I'm taking to write this way. But I could have written it like this too. I could have written the R2 is equal to the set of all ordered tuples x1, x2, such that I could have just written, such that x1 and x2 are a member of the reals. I could have written it that way. That would have been an easier way to write it. But either way, I think you get the idea. It's all of the combinations of two things. So I said in the beginning, I was like, this kind of is a squared operator. And why does it mean, why did they write it as a superscript there? And my gut sense is, if you think about it, in this, you have kind of an infinite. Well, look, you have an infinite number of real numbers. I mean, I won't go into things like accountability and things like that. But you have a very large number of real numbers. But let's say that you only had n real numbers, right? Let's say that we weren't dealing with reals. Let's just for sake of argument, let's say that you had like 100 real numbers, right? So that means that there would have been 100 possibilities there, and then there's another 100 possibilities there. So now your set of all of the possibilities of two tuples, well, you'd have 100 times 100 possibilities. So you'd almost have the squared number of possibilities. So however many possibilities you have for r, so you have that many squared possibilities for R2, which doesn't make a lot of sense because you have an infinite number of possibilities, but you have that many more possibilities. You have an infinite number of possibilities here and an infinite number of possibilities here. So it's almost a greater infinity of potential possibilities. Now, what's R3? R3 is just the same thing. R3 is, if someone wrote R3, that means you're going to have, you're going to have 3 points or 3 numbers. I want to be careful not to just say points. When we can graph these things, and for example, R2, points in R2 can normally be graphed on graph paper in kind of on just in Cartesian coordinates. Points in R3 can be graphed in 3 dimensions. Points in just R, or we could just say R1, you could just graph those on a number line. If I had to graph, I could have a number line like that. And if I had to graph pi, that's 0, I'd just say, hey, right there, that's pi. And if I had to graph e, I'd say, hey, right there, that's e. And if I had to graph 1, I'd say, hey, that's 1. So you could graph them, but I want to be careful that they don't have to graph them. They don't have to correspond to actual physical points on a graph. But anyway, when you talk about R3, you're literally just talking about all the possibilities where you have an ordered set of 3 numbers, where all 3 numbers are a member of the real numbers. That's all you're saying. Now, I want to introduce you to another definition of a vector. A vector. Now, a vector you've seen before. You've seen it in physics where you said, oh, it's something that has a magnitude and a direction. You saw it in calculus when we and we plotted them and whatever not. But I'm going to be very formal and very abstract and very broad with the vector right now, because I guess the beauty of linear algebra is that it doesn't just apply to things like physics, and it doesn't just apply, it does apply a lot to physics, but it doesn't just apply to that. In linear algebra, you can apply it to anything. It doesn't have to apply to things that, just graphs in 3 dimensions. And we'll talk more about that in the future, but that's why I'm trying to stay pretty abstract. So I'm going to define a vector in Rn. A vector to be in Rn. Actually, let me be careful. I haven't even defined what Rn is. I just defined R2 and R3. So let me define Rn. Rn is equal to the set of all n tuples, ordered n tuples. So you have x1, x2, all the way over to xn. So you're going to have n things. So if this was 100, you would have 100 things here. So you have, this is an ordered n tuple. This is an ordered n tuple such that for each xi, where xi is one of these, is a member of the real. So each of these has to be a real number. And then I'll just say for I is less than or equal to n, greater than or equal to 1. So all that's saying is that for x, x1 is a member of the reals, x2 is a member of the reals, all the way up to xn is a member of the reals. Rn is the set of all of these possible ordered n tuples, or ordered sets of n numbers. So what is a vector? What is a vector in Rn? Well, a vector in Rn really is just a particular instance of one of these n tuples. I'll just call it an ordered list. An ordered list of n real numbers. N real numbers. And you can represent a vector in a bunch of different ways. You could represent it, you could represent it like this. You could represent it. You could represent it like, well, let me do it in a bunch of different ways. You could, a two-dimensional vector, you could represent like x1, x2, kind of like a coordinate. You could maybe represent it with brackets like that. This is just syntax. This is just different ways of representing the same information, the same idea. And for most of what we talk about in linear algebra, we're going to represent them as essentially these columns, and in the very near future, we'll represent them as rows as well. But I'm going to define my vector. A vector is an Rn, is an ordered list of n real numbers, and I define, and this is an example. So it would be v1, v2, all the way to vn, where each of these is a member of the real numbers. So it's a member of the real numbers. And just to make sure you kind of understand the notation or the terminology, each of these is called a component. Component of our vector. And actually, I want to be very careful here, because when we write vectors, you want to make sure you have a nice bold v. I won't make all my v's in the future that bold. But that's how, when you're reading a math book, they differentiate between just a vector and just a regular quantity, right? These regular quantities are just written with a non-bolded, while the vectors are bolded. Now, I'm going to define two definitions for two operations for vectors in Rn. I'm going to define addition, and these are definitions. I could have defined them in any arbitrary way, but these I think you'll find to be somewhat natural. So these are definitions. Definitions. These are just kind of human abstract constructs that end up becoming very useful. So they said, hey, let's make some definitions. Let's define addition. Addition. So if I have some vector, let me write it as a lowercase a, but it's a really bolded lowercase a. And then that is equal to a1, a2. That's all of its components, all the way to an. And I want to add that. And then I have vector b, and I'm going to make that a really bolded b right there, is equal to b1, b2, all the way to bn. I'm going to define addition of these two vectors to be just the sum of each of their components. A plus bolded b is equal to a new vector. A new vector is equal to a new vector where you just add each of their components. It's going to be a1 plus b1 is going to create this new component, a2 plus b2, all the way down to an plus bn. And if you found this somewhat confusing, just think, I'm almost going through pains to write something very simple in very confusing terms. If I have two vectors in R2, let's say I have the vector 2 minus 1, and I want to add that to the vector 3, 2, I literally just add each of the corresponding components. So I add the first components to each other. So 2 plus 3 is equal to 5. Minus 1 plus 2 is equal to 1. That's all my definition of vector addition is for my vectors in real numbers. And now the next thing I'm going to define is the idea of a scalar multiple. So scalar multiple. You might remember from physics class, a scalar is just a regular number. Or if you're multiplying something by a scalar, you're just scaling it up. Maybe I shouldn't use the same word in the definition. But I'm going to define it as, let me say, c is a scalar. So let's say notice I didn't bold the c. So c times my vector a, and here I'm going to take pains to bold it up, times my vector a is going to be equal to all of my components of vector a multiplied by c. So a1, a2, all the way to an. And they're each going to be multiplied by c. So that's all I define. Every term is going to be multiplied by c. And just to give you an example like that, if I wrote minus minus 3 times some vector. I'll just draw the vector here. Let me draw a vector in R3. So let's say let's say the first term is, I don't know, pi. The second term is minus 2, and then the third term is 0. Then this is just going to be equal to, a new vector in R3, or you can kind of view it as a three-dimensional vector. Minus 3 pi, minus 3 times minus 2 is positive 6. And then minus 3 times 0 is just 0. So it's that straightforward. They made this fancy definition, but it's fairly easy to deal with, I think. And I'll just make one last definition. And I'll call that the 0 vector. The 0 vector. And depending on what dimension we're in, it just means a vector with all zeros. So the 0 vector in Rn, if it's arbitrary, is just a vector where everything is 0. And if this is Rn, you just have n components. So those are all my definitions. I think I've given you kind of enough to think about right now in this video. In the next video, I'm going to show a bunch more of examples. And I'll actually draw representations of these vectors, although you don't have to. And we'll kind of have a little more visual understanding of what they mean.